Hi everyone, my name is Bartek and I'm working as a software engineer at Software Mill, and today I would like to tell you a tale about math and scalability. And I would try to answer the question, can we in fact predict the scalability of our system by using mathematics? But first, quick acknowledgement from organizers. You can ask questions on Slido with this hashtag in the room 12. Okay, so let's start our tale. Once there was a system. It was quite a unique system because it was stateful. But it was working, it was earning money, so everybody was happy. The developers were happy, business were happy, company were happy, everybody was happy. But then, one day, company reached great marketing success, which caused the number of users growing in such big number to cause the system to crash. So, the smart developers who were responsible for maintaining this system knew that they can only do one thing: scale. Because there were quite smart bunch of people. They knew that they can scale vertically or horizontally. Because vertical scaling is, let's say, the simpler one and is, let's say, the default options for most of the system. They decided to go with vertical scaling first. So they knew that in this model, they can boost their performance by adding more memory, adding more CPUs, or by changing disks to more performance one. And they did it. They added more memory, they added more cores, but the results wasn't as good as they expected. So they started to ask why. And they started digging and searching and looking for a reason. And their research brought up concept known as a contention, which can be described as a competition over the access to a shared resource. And as every competition, it can only have one winner. And in our world of software engineering, it means that all the other processes or threads they want to access particular shared resource are effectually wasting the resources assigned to them. So our developers came to the conclusion that it limits their system scalability in quite significant way. So they started to look for a way to calculate or estimate the impact of this contention concept on their software. And after some additional research, they found out that yes, its impact can be evaluated thanks to the Amdahl's law, which is a law from a border of mathematics and theoretical computer science, which describes the theoretical improvement in latency of task execution under the fixed load in the system whose resources are improved. So in plain English, it can be used to calculate maximum improvement gained from adding more resources to the system. And here you can see the equation for Amdahl's law, with S being the overall improvement in execution time, N being the improved resource, and G being the proportion of execution time that the part not benefiting from improved resources originally took. It's quite cloudy definition, so let's make it more descriptive with an example. Let's assume that we have a task in some arbitrary system, and this task have two parts, multi-threaded and single-threaded part. And we want to scale up its performance by adding more threads. Then G will represent the execution time of single-threaded part compared to whole task execution time, as single-threaded part in any way does not benefit from adding more threads. It will still utilize this one particular thread. And there is also an alternative equation for Amdahl's law, where parameter G is replaced by 1 minus P, with P being exact opposite to G and representing proportion of execution time that the part benefiting from updating resource originally took. Going back to our example with a task and multi-threaded and single-threaded part, P will describe the multi-threaded part execution time compared to a whole task execution time, because this part benefit from adding more threads. And here you can notice the plotted graph for Amdahl's law. In fact, it does not give us many useful informations. That is why I decided to add a line representing the linear scalability. So let's say this perfect stateless model that we at least want to achieve. And now you can notice the impact of contention on the system. But let's go back to our tale, where developers, after initial checks and calculation, decided that there are some optimizations needed. And they did it. And after them, system scaled pretty well, until it stopped once again, because why not? And maybe company reached yet another great marketing success, or through a gossip protocol, many users starting to join the system with their numbers once again breaking the critical mass and causing system to stop. So the smart developers came to the conclusion that they probably reached some limits over vertical scaling. So once again, they knew that they can only do one thing, and one thing only. They will have to go horizontal. But it is not that simple. In fact, making a stateful system able to scale horizontally, it is one of the most complex tasks which comes to my mind in our world, next to choosing the correct naming conventions. In this case, the developers will have to make changes in the code, make changes in the architecture, and reorganize the whole infrastructure responsible for maintaining and deploying the project. But They like their job, they like their company, they like their salary, and it had to be done. So they did it. And the system was ready to be scaled horizontally. So they added a node, or 2 nodes, or a lot, because what bad can happen if we add 100 nodes to the system? Nothing, of course. But guess what? Performance decreased instead of increasing. And everybody in the office was walking with this strange, surprised look on their faces and asking this one question: how can performance decrease after adding more nodes? So the whole research phase started for once again. And after some time, it yielded results in form of consistency and coherency delay, with the latter two being the probable main suspect of their strange behavior after adding more nodes. Let's start with a quick recap of what is consistency. And it can be viewed as a dealing with order of reads and writes to ensure that they will be seen in order that make sense. And this is one of the most crucial problems in modern system engineering. It is also the part of the CAP theorem, and as a side note, the most common consistency models nowadays are eventual consistency and strong consistency. Okay, but what is coherency delay? It is not so popular concept like consistency, and it can be viewed as the time required to reach system-wide consistency. And during their research, the developers found out that its impact can also be evaluated thanks to the Gunther's law, or as you may know it, universal scalability law. It is yet one another law from a border of mathematics and theoretical computer science, which is built atop Amdahl's law, but it also accounts for overhead due to inter-process communication. So in plain English, it accounts for coherency delay. And thanks to this fact, we are able to see more real-life-ish results of our attempts to scale up the system, and we are even able to see the negative results of adding, for example, more threads to the system. And here is Gunther's law equation, with S being the overall improvement in execution time, and once again being the improved resource. Parameter G, same as in Amdahl's law, representing the proportion of execution time that the most node benefits from improving resource. And new parameter K, being the proportion of execution time that the system spends on achieving consistency. So K represents the coherency delay. And here you can see the plotted graph for Gunther's law equation. In fact, it gives us one interesting insight. As you may notice, the biggest improvement in performance we get around adding 2 nodes. So after in the three-node system, our performance is the best. But there is the last graph for today, where you can see all the lines from today's talk with linear scalability in blue, Amdahl's law in red, and Gunther's law in green. And now you can notice and compare impacts of both contention and coherency delay. And you can even notice the difference made by the coherency delay itself. But let's go back to our tale for one more time, where the developers came to the conclusion that number of nodes that they will add to their system is quite crucial. Besides giving them the best performance, they will also know what amount of resources to prepare before day one. They will be able to estimate costs of cloud providers, for example, which business for sure will be happy to have such a knowledge. And what is even more important, they can estimate how far the system will scale in its current state before any code changes will be necessary. So they will know if their system is able to handle their current production load, which is very good piece of knowledge to have, because nobody never wants to fail on day one, quite obvious. So they notice that Gunther's law is just an equation for function. And they are interested in getting the maximum value of this function in a given subset from 0 to some arbitrary n. And they are already made equations for that in mathematics. And here it is for this specific law, where p being the optimal number of nodes, which have to be full number because we cannot add 2.5 nodes to our system. G being the proportion of execution time known from two previous equations, and K once again representing the coherency delay. So, as the tale is coming to an end and the release day approaches, the developers were able to make all the needed optimizations or the needed calculations. And when the release day finally came, the system was working. And everybody was happy once again. Business were happy, developers were happy, whole company was happy. But there must be always some but in software engineering. Here is the real world, and we have last one question to answer. Can we predict the scalability of our systems by using mathematics? And the answer is yes, we can. But it depends, unfortunately. The biggest benefit of both laws is that they have no dependencies to underlying architecture. So they can be used to calculate the impact of adding more threads, CPUs, or memory, or other stuff even. But the main issue which virtually renders both the laws 0 to no use in the most common cases in software engineering is that parameters G and K are measured by experimentation. There are no set rules, principles, or example value of both the parameters, depending on your system, grade, scale, or choose architecture, for example. But because we trust in math, it gives us some other solutions to our problems, like queuing theory, which is the part of mathematics researching the behavior and interactions or queues, quite simple. Or in more mathematic style, lines. And it contains already made equations for example, throughput, which we can use to calculate the same as universal scalability law. So, unfortunately, it is a topic for yet another tale. And now, few words of summary. Systems need to be scalable. It is an obvious fact. We need our systems to be scalable. Contention and coherency delay are both facts of life, and we are unable to run away from them. They will find us, and they will bite us sooner or later. Or maybe they're doing it now, and we don't even know about it. Amdahl's law can be used to calculate the impact of contention, while Gunther's law takes coherency delay into account. And we can use Gunther's law to calculate optimal number of resources to add. So, thank you. If you want to stay up to date with what I'm doing, you can find me on Twitter under this handle, on LinkedIn, on Software Mills blog, and on DZone, where I'm trying my skills as a writer. Now let's move to Slido to check if there are any questions. Okay, if my Slido is working okay, there are no questions for this talk. I don't know if I'm right or wrong. I'm right? Okay, so thank you for your attention. Have a great rest of the conference and have a nice day.